Okay, testing sound. Yep. Have you done it before? Have you done it before?
Yeah, earlier today.
Oh, okay, great. Yeah. Okay, it seems that the sound is there. Could be louder. We'll increase it here. Be louder. We'll increase it here. Be louder. What are you cutting?
I'm making this a panel for the Eurorack synthesizer.
Okay,
Yeah.
good. Ah, that's nice.
This computer reminds some virus thing like all the time. I'm just going to put later, right?
Yeah, or select the checkbox and 4 hours just
Okay.
to choose the maximum. For I don't know what this antivirus craziness. Sorry?
I set the temperature to PLA, but then when I printed it went to 140.
Yeah, because like it's defined by G-code.
Okay.
So and then yeah, it's trying to match. And for the 140, it's only it's gonna clean the nozzle and then calibrate, and then it's gonna heat up to PLA to 220. So that's all pre-programmed in G-code. Okay, seems that audio is all right now. I could optimize it a tiny bit, not the absolute maximum, so I think this is now much better. And let's try to set up other things. So KiCad, Pcb, then we need EU, no. We need this. Okay, this is it. Yeah, be careful. So this is off. This was off.
Oh. Yeah. I thought it was just that one.
Yeah, and in this case, close the door.
So it's this one?
Yeah.
Which one? This one?
Yeah, it has to be to the maximum.
Okay.
Yeah, use this to clean it up. Yeah, be careful. It's don't go in there yet. It's full of fumes. Come here.
What the hell? What's happened?
No, the ventilation was turned off suddenly because of the stupid switch. So take this.
The switch wasn't on?
Yeah, because it's. I mean, it's because like whoever installed it is a dumb motherfucker.
So the vent just went off. Maybe,
So okay.
I'm gonna take one of these hooks and open the windows.
So that's from that. There's like a funky switch, so it's a timer switch, and then not everybody is turning it on to the maximum, and then it expires and the ventilation is being switched off. It's a very stupid one. So yeah, I'm building a small list about kind of a reference for myself what we are going to go through?
Yeah.
Okay. You watch me. Good. Okay.
So the open day is every Thursday from now on, or?
Yes, every Thursday, and then yeah, today we discussed it from April. We could have also open Saturdays because it's end of the semester, and the students they want to finish their work, and so we could be here also on Saturdays. Hello, hello. Yeah, we're gonna wait for 5 more, maybe 10 minutes to so that usually people are a little bit late, and then we will start. Somehow it seemed that this week is gonna be more people and a bit more also different, like other kinds of people. So usually somehow it was that they were the same, but you are new. I think like electronics design is something very specific, so most people perceive it as something really complicated, almost like rocket science. It's not the case. I mean, I think like the most complicated part is the naming conventions involved. That there are so many naming conventions that it's really hard to navigate the parts. Yeah, but once you get into the terms and into the naming conventions, then it gets easier and easier. So yeah, basics of electronics. It's people explain it in so many different ways. So I couldn't tell that I'm the best explainer myself, but I'm trying to get there. But it's nothing too difficult. Also, it's like flow of water. Louder. Okay, let's try to make it louder. So this is, I cannot really get louder than that. So this is the maximum. The mic is pointing away. So how can we fix that? So this is, must be better now. I hope so. Okay, it is better. Nice. Thanks for remote support. So very useful. Wait a minute. So finalizing PCB design. Camera. You wanna? What? Wait. yeah, it should be visible now. Yeah, that's the one camera, and then there's the one that is pointing at me. Okay. But I cannot see myself. Wait a minute. Did I switch something off? No, it is showing me. Need to refresh the page, maybe. Ah. Now it's there. Yeah. This camera. One more test. Okay. Okay. So if you haven't downloaded KiCad yet, then you can go to the KiCad website. So with me, it was that there was an issue. So when I downloaded the latest version, then it was a bit it was buggy. So whenever I wanted to do something with a library manager, then it crashed. But there's a solution to that. I tried to download the nightly builds. I think the one I downloaded was from February 24, so you can use that. So it's 1.2 gigabytes. It's quite a lot. So it will take some time. But I think like the internet connection here, at least, it's quite good. It should take you not more than 10 minutes maybe to download. But if you have it, then no worries, no problem. Yeah, so Fab Academy Thursdays is an activity that I started in order to advertise the Fab Academy at the Alto Fab Lab a little bit, and also iterate on my skills related to being able to explain some basic things about the things that are being taught at the Fab Academy. And the Fab Academy Thursdays, they generally follow the schedule that is available online, the schedule of the running course. So as you can see, it started January 16, and yesterday there was the last global lecture, which was about electronics design. And this is why this Thursday we have introduction, so electronics design with KiCad lecture. And if we take a look at the electronics design page of the official course, so nothing is hidden, so there are no passwords. You don't need special access in order to be able to access this website. It has like a list of things that are normally covered by the course. It's quite a lot, but if you are a beginner, then it might be really hard to get started, and this is why we are going to talk a little bit about KiCad today. And usually a lab should have parts, electronic parts that are in the official Fab Lab inventory. So there's not just electronic parts, but also other ones. Wait a minute, resistor. Yeah, so here, for example, so the inventory that advertises to purchase parts from DigiKey, but there are also other places where you can buy parts, like Farnell and Mauser. So today, for today's exercise, I also got parts from DigiKey. Yeah, and you see that there's this keyword SMD, which basically translates to surface mount technology, and it is a type of a component that can be mounted, that can be put on top of a circuit board and easily soldered with the help of machines. So the surface mount technology is more about the possibility to automate electronics production. And yeah, the other thing that you see in the inventory is that so there are these numbers, so 1206 for example, that relates to the size of the components, and I think it's in thousands of inches. So if you translate, so 12 mil to millimeter, wait a minute, what was this? Okay, it's 0.0 inch. Okay, so if you go from inches to millimeters, then 0.12 is 3 millimeters, and then 0.6 is 1.5 millimeter. I could actually show you one of the components, one of the resistors. I'll just quickly find one from the inventory here. So I'll switch over to this other camera. This one. Yeah, usually they come in these kind of strips. So for they have so the parts in these strips, they have regular intervals. This is for the pick and place machines. So when you program a pick and place machine, then you can specify the distance between the components, and then the machine will know the increments that are needed in order to pick up a certain component and place it in the right position. And yeah, if we take one of those, it looks like it is 3 millimeters. It could be the right size. I think it's, yeah, 3 millimeters by. Oh, let's take a ruler in order to find out. Where do we have these rulers? So here is our components. It's really hard to grab. Yeah. And then, yeah, it is 3 millimeters. Okay, so that's that. This is like my little plan for today. Yeah, if you want to apply for the Fab Academy here at the Alto Fab Lab, then feel free to communicate with us. But today we are going to dive into KiCad, which is electronics design software. It is open source and free, and it's strongly supported by CERN, by the particle physics laboratory between Switzerland and France, was it? Yeah, and so I already told you that it would be nice to get the nightly build if you are on a Mac computer. I heard yesterday that some people had problems with Windows installation, so it might be a good idea to download the nightly build for Windows as well. And we are going to build a circuit using the 555 timer. So usually the basic circuit that you usually do when you learn basic electronics is a BLINKY, and there are many ways how to do a BLINKY. One way is to do it by using a 555 timer, which is an integrated circuit, which makes it easier, and it also teaches you a little bit about how to use a integrated circuit in your design. I'm going to get parts from DigiKey. It's not an advertisement, sorry, DigiKey, but yeah. So we are going to cover the schematic design in KiCad. Then we are going to add some existing parts like resistors and capacitors. Then we are going to cover creating custom symbols. So something that is easier to use with the circuit that we are going to design, which we are going to look up on the internet. And then we are going to finalize the schematic, export a netlist, and then enter PCB design process. Then create custom footprint for the parts that do not have a footprint yet. And then we are going to add this custom footprint to the PCB design, and then we are going to finalize it. And then hopefully we are not going to run too much out of time. We are going to try to prepare the design for milling with the Model MDX machine that we have here at the lab, using Fab modules, and we are going to save the toolpaths for the machine. And I think I will need like around 5 to 15 minutes to set up the camera next to the machine. So it might be that we are also going to mill the board at the end of the process. So yeah, let's switch over to KiCad. So this is the KiCad site. We looked at it already. And this is the 555 timer integrated circuit. So there are many ways how you can use this, and this time it's just going to be a blinking light, and they come in many flavors. So there you can get versions that are compatible with high voltages and not so high voltages, and more current and less current. But today we are going to use a low voltage one and low current one, and instead of using this like through hole component, we are going to use a surface mount one. So actually I will just show you What I mean by that, so I have a data sheet of the 555 timer that we are going to use here. So LMC 555 CMOS timer. So go figure what all the parts of it means, but maybe over years you will understand every part of it. A lot of specifications. There should be a drawing of it as well somewhere. Or not. This is the package. Yeah. So this is how it looks like in the drawing. Yeah. So it has 8 connectors, so surface mount connectors, and we are going. And normally you connect these connectors with a solder to the printed circuit board. Here is like a nice little rendered image of it. So yeah, this is how it looks like. There are other versions of it. Yeah. Then I have some also here in the box. So if here, which ones were they? I think it was this one. So these are from DigiKey. And they come in such a strip, and as you see, they are smaller than my fingernail. Yeah, that's about that. What else? So then we are going to use a battery also and a potentiometer, but let's get to the circuit. So there's apparently like 555 timer is a very popular one, and there's even a website which lists many ways how you can use it. So here, yeah, you can use it for amplifiers, metronomes, anything that you see on this page here. But what we're going to make, we are just going to make a flashing LED. And this is the circuit that we are going to use as a reference. And as you see, it has, so here it uses 9 volts, but we are going to use 3.3 because we have 3.3 volt batteries, so really low power. Then this is the timer itself. There are 3 resistors, a capacitor, and an LED. Okay, so what do we do now? So in order to start to design it, we need to start KiCad. So I will go to my applications folder, and we need to start out with this KiCad app. So it's at the beginning, it opens up this window, which is kind of an overview window. Where you have a list of projects that you created before with KiCad, and the first thing you want to do is to create a new project. And in order to do that, you go to New Project, and let's choose. So I will make a folder for KiCad BLINKY and call it BLINKY, like, or 555 BLINKY project, like that. And it automatically created me a schematic file already and a KiCad PCB file. And what we need to do now is we need to open this schematic, and it is going to open this weirdly looking page. So you don't have to really use this grid always, but somehow it is here by default, and it is there for a bit more complex circuits. So for example, if you have many parts and very complex structure, then it and you are collaborating with a team, then it makes sense to use this grid in order to find a specific part in the circuit, in order to be able to find a specific component and a specific problem. And then here, yeah, you have all kinds of other things for being able to share the circuit with other people, and then later on people would know who is responsible for it, and so on and so on. But yeah, so the most important things in terms of circuit design you see on the right and left side. On the left side, yeah, you can turn the grid on and off, so it's nicer to use the grid at the beginning. And it's also enabled by default. Then you can set the units. It should be millimeters, unless you are working in the US and you use inches, and everybody else around you uses inches. So yeah, unless that's the case, then use millimeters. Then so this is for drawing lines and connections in, yeah, I think like in straight angle fashion. Yeah, to be honest, I don't know exactly what it means, but okay. And then on the right side, you have different kind of tools. So the most important one being the place symbol one. So this is what you use in order to place symbols in your circuit. Then, so this is for adding power ports, which is an important thing for any circuit. So it's not going to work if you don't use any power. And then this is to place wires in between the components. Then these are more like advanced things. So you use this one in order to indicate pins that are not going to be connected anywhere, so which is important for the electronics rules check. But today we are not going to dive into that. So here you can place junctions. So you can add labels. So you can add the global labels. So sometimes instead of using wires in between components, they are very far away from each other, and it makes sense to connect them using labels like these. But okay, let's get going, and let's start placing components according to the circuit that we have. So let's maybe drag this in the other screen. Yeah, like this, and put it like this next to the window. Yeah, I also activate the mouse position. No. And let's check. Yeah. So you will see what I am pressing. So this is the middle button, and when I press and hold middle button, and I can pan the view around. Then if I use the mouse scroll, yeah, mouse wheel, then I can zoom in and out. This is left click, and this is right. No, this is right click, and this is left click. So the yellow one is middle click, the red one is left click. Like normally you would click with the mouse, and then the green one is right one. And yeah, in order to place a symbol, you can hit the place symbol icon, or you can also hit A to add. Like KiCad heavily relies on shortcuts. And A stands for add component. And so we see, so I think the most common component in any circuit is the resistor, and we can find resistors in any like circuit CAD software, and so in KiCad we can find it by just typing R, and it's gonna give us the generic resistor symbol. All we have to do, we have to click OK, and then place it somewhere, click somewhere on the on the circuit in order to place it. And then we can add another one by repeating it, just clicking again and double clicking and placing it in the circuit, yeah, like this. Yeah, the next thing that we would like to add is a capacitor. So let's hit A one more time and enter C in order to find a generic capacitor. Okay, and then click anywhere in order to place it. And another thing that we will need is an LED. And again, I hit A in order to add an LED. And here's a generic LED symbol. And I will just click this select item icon in order just to navigate and to be able to select items and move them around. So it doesn't work really as a regular drawing software usually works. You cannot really select these and pull them around, although you can just yeah, you can select them by using this rectangular select and drag them around the screen, or you can hover them and you can use the M key, M shortcut, in order to grab and place them somewhere else. Like M stands for move. Another thing that you can do, so when you have it on your cursor, then you can hit R in order to rotate it. So in order to align it in the same way, rotate it in the same way as it is in the circuit, the reference circuit, we'll have to hit R one or more times, and then you click with your mouse and place the component, and it is there. Yeah, and so the 555 timer, so that's the custom part schematic symbol that we will need to create. We are going to try to create in a similar fashion as it here in the example circuit. And in order to do that, we will need to enter the create, delete, and edit symbols part, or like the symbol editor, the symbol yeah, editor. And so as you see on the left side, there are many libraries that have all kinds of components already. But what we are going to do, we are going to create our custom library. And for that, we are going to go to File, New Library. And yeah, going to call it the same as the project name. So 555 BLINKY library, like that. Hit save. And for this, we don't want to be global because like it's going to be very specific to this project. So we are going to select that it should be only for this project and hit OK. And now we should have it here. And we can right click and select new symbol here in order to create a new symbol, or we can go to File, New Symbol. And we are going to create a 555 timer entry here. So the reference designator, we can leave that empty for now. Number of units per package 1. Yeah, we can leave these two as default. So yeah, and as you see, it automatically creates the symbol with its name and reference symbol, so this U. And we can use this editor in a similar fashion as the schematic editor. So we can hit M and put these a bit off from where we are going to work. And I'm going to minimize this so we can see the reference. And when we are creating symbols, then the most important part is to add pins of the symbols. So every integrated circuit has a certain amount of pins, and in this case, it's so we have this one which has 8, and one of them is not connected. And let's just start by clicking this add symbol icon and click anywhere on the canvas, and let's give it a name. And for the naming, we'll need a data sheet. So let's switch over to the data sheet. Where did we have it? Here. No, not a data sheet. This is going to be the data sheet somewhere here. Did I have it open? Yeah, actually I did have it open. Here we go. Somewhere here. Yeah. Just gonna make it a bit smaller. Somewhere in the beginning of the datasheet file. Sidebar. I think it was it with all the names, but I'm still hoping to see something that is a bit more. Or we can see it on the Wikipedia site maybe. Here. Yeah, here we go. So this looks much better. This one. And open a new tab. Yeah, but this has a black background. Oh no, it's not what I want. Where is it? Here. Okay. So we'll need to add the pins. So let's start with ground, which is number 1. So GND, pin number 1. Don't mind these electrical types for now. So we are just going to do it in a really basic default way. So as the ground one is, so you leave the orientation to right for now. So it's gonna be available on the right side. Click OK, and yeah, and place it anywhere on the canvas. So when you will add this symbol to the actual circuit, so you will be able to connect wires to these points which are which have circles around. Yeah, so these should be somewhere outside the circuit. So let's add another one, number 2. Then another one, which is going to be number 3, which is going to be out. Okay. And reset. Apparently there's a trick to add overline over it by using this tilde letter, but I'm not sure why exactly. Still. And then on the other side, you will have VCC. Here we can flip sides in order instead of having it on the right. Let's choose the left. Which is So inputs, and then this, so discharge number 7. I forgot to add a number here, but in order to change something about the pins, you just need to hover it, and then you can hit E, and it stands for edit, and then you can just add the number afterwards. The same goes with moving. You can just hover the component and you can hit M and move it. Then activate the tool again. THR number 6. Okay, place it. One more. Let's see. Control number 5. Okay, and place it. And now let's arrange it so that it matches the circuits that we can see here. So we see that, zoom out a little bit, and so you can move multiple pins by using, first of all, selecting the select tool, then dragging a rectangle around them, and this is the way how you can move it around. So you can click and drag in order to draw this rectangle around the pins, and then it automatically starts to move together with your mouse cursor. You can do it with individual pins as well, or you can just hover them and hit M in order to move them. So let's see, let's start with number 7. So we need it somewhere here on the other side, and as we see, it has a connection on the left side, so which means that it's the, I don't know, the orientation should be right. I don't know why it's exactly right if it's on the left side. Yeah, then we can continue with number 4. I think we can just use the rotate tool in order to rotate it like this. Then number 8, also a rotation tool like this, and then number 3, okay, then number 5, it's gonna be on the bottom, and number 1 after that. Let's also grab this U letter, like this, and number 2 is gonna be over here, and then number 6 somewhere in between, like this. And now we can also arrange it in a bit, add a bit more spacing to it, that it looks also closer to what we see in the reference circuit. Number 2. Number 4 we could move also a bit to the side like this. Hey, I also want coffee.
Coffee?
Yeah. Okay. And now at this point we can also So we can also define an outline by using the rectangle tool, and yeah, there are no real rules for how you should define that, but I mean, I think when you make it so it snaps to the pins, then that's basically it. That's basically what you need to do. And then 555 timer, we can put the name somewhere here or maybe on the symbol itself, and then review. Okay, and it seems that that's it, and we can actually go to File, Save, and it's going to be saved in our library. Now we can close the symbol editor, and here you can again click on Place Symbol icon in order to place it, and let's see, BLINKY. So we don't see the library that we just created here, and which means that we need to symbol library browser. So where was it? We need to add the library to the project. But let me remember how to do that. Symbol library editor. BLINKY, add library. Already exists, but then was it in the browse symbol libraries? 555 BLINKY. Or was it indeed here? Ah, here it is. Yeah, 555 BLINKY library. It's already added. Hit OK. And now we can place the symbol in our schematic like this. And we can start working on the wiring. So we can, yeah, so we can place these according to what we see in the reference design. And in general, a good idea is to try to keep them as far away from each other as possible. That's going to make it easier to do changes and see where things should go afterwards. But in this case, it's very clear, so we don't have to worry about that too much. It's just that let's lay them out. Nicest possible fashion, and then at this point we can start using the place wire tool. So when you click on this icon and then you click on one of the pins, then you can start drawing a line, and the line is being drawn by clicking once, then dragging the cursor to another location, clicking one more time, and then the wire drawing stops when you click on the other connecting pin, like in this case. So when it meets a place where it should be connected, then the drawing automatically stops. But we are still using the same tool, so you can actually just continuously click and place the wires. So number 3 would go here, here, and then there. And then number 5 is not connected. This will go here, here, here. Capacitor is going to connect over here. Resistor to capacitor, the other resistor to other resistor. In between these two resistors we connect pin 7. Then we want to connect this one to pin 6, and then this one to the wire connecting to pin 6. Yeah, and as we see, the number 5 is not connected, but in KiCad we need to use this place no connection flag tool in order to tell that it's not going to be connected. So this is fine. And now, yeah, as we see in the reference design, so there are 2 pins which stand for the power input, and we need to define some power symbols for the circuit, and for that we have this tool here, place power port, and yeah, we'll need 3.3 volt power flag. So I just started to type 3.3, and it gives me the necessary symbol that we want to use. I just double click, and then I place it somewhere in the circuit. So this is going to be for the positive voltage, and then for the negative one, I'm just going to click again and look for ground symbol, G and D, and place it somewhere here. And with these symbols, you can do the same as with any other symbol in the circuit. You can just grab it, move around, and then you can rotate it like this. And also, thank you. Yeah, and then you can use the wires in order to connect them to the circuit, like this. But this is not it. So, okay, we have these virtual power flags, but what do we need? We need also the battery input. So we need a specific part that specifies a battery, and we have those here in the symbol library. So I'll select the place symbol tool again and click somewhere here and type bat. So yeah, battery cell, single cell. So we'll use a single cell battery. So this is why we choose this instead of the multiple cell. So single cell battery, okay. And we put it somewhere here like this. And it has pin 1, which is plus, and pin 2, which is minus. And we can use the wire tool in order to connect it to our circuit as well. Like this. And at this point, let's save it. Have a tiny bit of coffee. Do you have questions? Are you following along?
Personally, my KiCad keeps crashing, but I tried to update it by just deleting the old one and installing a new one.
You tried the nightly build?
No, I think I put the last stable one.
Yeah, well, there was a problem with the last stable one.
Oh.
Yeah, it was crashing for me as well. But if you go, so if you go to the KiCad website, so here, so Mac OS, here are the nightly builds. So the one from, I think it was from 24 or 23rd of February, it worked.
Okay.
So I checked the forums, and there was a bug, and apparently it was fixed, but then, yeah, it's only fixed in the nightly build, not in the stable version. Yeah, actually, it would be interesting to know. So I did forget to ask about your previous experience with KiCad and circuits?
I'm pretty experienced with circuits, but not with KiCad. I checked some videos and started Q1 project, but it's still, because I'm used to like more like the graphic design, so this is a totally different type of thinking about these things.
Yeah.
So now it seems really easy because I'm following you, but when I did it myself, it felt really hard to get into the logic behind that software. Yeah.
But then, so what I can recommend, so I got this knowledge, I learned KiCad from there's a guy who is making a course, Contextual Electronics, and it's an online course, longer one, and it's all done in KiCad. So, and you can, yeah, I think I want to go through it myself. But it just seems like, so far as I've been following it, that it's a great course. It's I think like a good place where to start. Because I think usually there's this missing link. So whenever I buy and start reading an electronics book, it's full of symbols and theories and all that, but then there's a really wide gap between this knowledge that you read in the books and about practical applications. So nobody mentions any CAD software that could be used for contemporary electronics in these books. It's good for theory, but then it's really still like quite far from getting you started. Yeah, and at this point we are actually ready to create a netlist. And in order to do so, there's a button here, generate netlist. So click on that. So you can leave the defaults here, and you should click on generate netlist, and the netlist is going to be saved as a file, so which is interesting. So every part of KiCad, so whenever you are creating something new such as a netlist, it's going to be output as a file. So yeah, it's a program that consists of many smaller programs, and each of these smaller programs has its own file format. And then these programs depend on each other by sharing these little files. Yeah, and then another thing, so it's asking me about annotating. So in order to be able to create this netlist, it needs to fill these question marks with numbers. So this is resistor, but which one is it? So KiCad needs to assign it to something. It's going to start annotation by sorting from left to right, and if you added any manual annotations, then it's gonna keep that. And yeah, you hit annotate, and then you see this R question mark becomes R1, then R2, R3, U1, C1, D1, battery 1, and so on. And now we have the netlist, and after creating the netlist, we'll want to create PCB. And for that, before we do that, we need to assign schematic symbols to footprints. So for that, we click on this tool. It's going to bring us to the assign footprints editor. So in the schematics editor, we only have the common electronic symbols here, but then on the board we will have something like this. So these guys, so like pads, copper pads for soldering to components on them, and these have physical properties like width and length and position in space. And so in contemporary electronics, there are many standard packages already, and I think software like KiCad and Eagle, they are trying to cover all of them. And what I like in KiCad, which I didn't really find easy to use, or I couldn't find it so easily, is that KiCad offers you a really long list of relatively nicely named footprints that you can use in your designs. Yeah, and here in the footprint assignment editor, you can see that on the left you have the libraries that are available, footprint libraries, and then in the center part you have the mapping. So just the symbols, they have numbering. Then there's the name of the so the annotated name of the specific component, and then on the right side there should be something. There should be the footprint name, and the C1. So it's the capacitor in our circuit. Wait a minute. Yeah, capacitor. And so it's an unpolarized capacitor. So unpolarized capacitor, let's just look it up on the internet. These are usually ceramic. Yeah, they look like this. And they usually have value in microfarads, and so it's how much current they can keep in them. And then they also, for SMT components, they have size, and we are going to use the size recommended by the Fab Academy, which is 1206. And here on the left side, we can just look for capacitors SMD. So this is the category. And here, yeah, we can see that there is something already. So there's capacitors SMD C1206 hand soldering. So you can double click on that, and it assigns it to the symbol and automatically jumps to the next one. And in this case, it's an LED. For that, we need to look for LED. And an LED, SMD LED, is going to look approximately the same. And it also has the same sizing. Yeah, like this, for example. The same sizing convention. So LEDs here, LED 1206 hand soldering. Okay. Then 3 resistors. So for those we can select the same, but we need to go to the resistor category. Resistors SMD 1206 hand soldering. Double click. I'm gonna do it 3 times, and then 555 timer. So fortunately, we don't have to create the footprint from scratch, because the 555 timer itself is packaged in a standard package, but we just have to find out which one of those it is. And if we scroll down in the data sheet, then we should be able to find a name or some hints towards the type of package that is used. Package outline SOIC. So I think that, yeah, this is SOIC. Package type with 8 connectors. So let's try to look for something like that. So here we have a SMD packages category, and for the footprints, let's look for something that has, yeah, so here we have packages, SOIC package type, 8, and let's double click that. And so for the battery cell, so I have selected a specific battery holder, and I couldn't find this footprint in the KiCad library. So this is also good, because this is going to give us an opportunity to design a footprint from scratch. So here, battery holder data sheets, preview. Yeah, so this is our battery holder, and it has a PCB layout footprint with all the measurements already there. And this is what we will need to design specifically and assign to existing schematic symbol of the battery. And at this point, we can click apply, save schematic, and continue. Schematic saved. Okay. Okay, so did you follow any questions so far?
I don't think I have all the libraries. I can't find any of those.
Okay, let me take a look.
Any?
Ooh.
Did you let it download the thingy?
Probably not.
Because it asked me, like, do you want to import the existing library?
I have a finished version. Maybe then, maybe you downloaded the plain version without any libraries.
Yeah, it could be. I'm not sure.
Yeah, but if you downloaded one of the recent versions, then I think it should be there, because for me it was there automatically. But maybe.
Can I find them from the KiCad?
Yeah, if the interface would be.
Is that, like, understandable?
Yeah. I mean, if it were English, then I could.
Symbol, edit symbol.
Yeah, I probably don't have it.
Let's see. Symbol, browse symbol libraries. File.
I don't know how you import them.
There was something. Maybe you need to go to this main page here. And existing project. CD calculator.
There's a manage symbol libraries in the first window you open. Like when you, before opening a schematic or a PCB, if you go to that window, and then there's preferences, manage symbol library.
Ah, yeah, there is this manage symbol. Okay, and here you can include all of those. Yeah.
So where?
So when you go to the main window, so when you open this one, you go to preferences, manage symbol libraries, and here they are. Yeah. Can you see them? If you don't see them, then maybe you need to add these. Here are the custom libraries. Project specific. No. I think there was a place which I saw at some point that KiCad is trying also to download the library from GitHub directly. Did you find them?
No.
Yeah?
No.
No, they're not there.
So this is preferences, and it doesn't have that. I think.
You can download them from the KiCad website.
Website?
The libraries.
Yeah.
That's
Yeah,
weird. Maybe it's another version, maybe.
Well, maybe I'll
Edit,
just download the library.
edit package on PCB.
Yeah, the slash libraries.
What is that?
Information about KiCad.
It just looks like a completely different version.
Yeah, I haven't downloaded like the used one.
Okay, but still, it should be somewhere available.
I'll just try and find it.
Okay. And yeah, for designing the PCB, we will need to enter the PCB Layout Editor. So with this button here, so we click on that. It's going to open us another window. So what annoys me a bit about KiCad is that it has like these so many different windows, so that you can really get lost. And would be nicer to have it somehow organized in a better way, but maybe in the future it's going to happen. So yeah, so this is much closer to a drawing software than the Schematic Editor, because this has all the layers. So you can, if you have used Photoshop or Illustrator or CorelDRAW or any like Inkscape or GIMP, these kind of softwares, you know the concept of layers, and this is similar. So, but instead of just having layers for colors and different types of objects, so this has special layers for the copper traces, then for solder paste, for adhesion, for edge cutting, holes, and solder masks and silk screens and all the things that are used in the PCB production technology. But what we are, and then by default there are also front. F stands for the front side of the PCB, and B stands for the back side of the PCB. So in case you want to make a double-sided or multi-layer PCB, so this is by default just set to 2 layers, but you can set it to more. But we are just going to use one side, so we are going to use this FCU, which is the front side copper layer for placing our components, and then we are also going to use the edge cuts layer in order to define the borders of the PCB. And in order to start to create our PCB, we need to import the netlist. For that, we have a load netlist icon over here, so we click on that. We need to specify the netlist file, which is the blinky.net file that we created in the schematics editor. Hit open, and it cannot find footprints for some reason. Okay, let's close this and try again. So what is wrong? Okay, here we go. Let's open the schematic. Maybe after assigning the footprints, go to save schematic, hit OK, and then I need to export the netlist. And now I generate the netlist. I will save it here. I will replace. Now,
can you explain a bit again? Like, what's the netlist? Like, what does that?
So the netlist. So the netlist defines the connection between the schematic. So these schematic components,
Okay.
so these symbols,
Yeah.
to actual footprints.
Okay.
On the PCB, so which are these pads that are going to be cut out of copper.
Okay.
And there are standard ones that we found by using this. Where is it?
Yeah, the libraries that are there.
So this one.
Yeah.
So the libraries that are there, and then we are also going to create custom ones.
Okay.
So I think that the creation of the custom ones is a really useful feature. I always wanted to learn that, and finally I know how to do it.
Yeah.
Because sometimes you get these exotic packages, and you do not necessarily want to load a library of 10,000 components only to use one specific component. You better create your own library with a few components, and these are the only all the components that you need. So that's a nice feature, and as you saw, it's not that complicated to create your symbol, and it's not that complicated also to create your footprint, actually. So now, so yeah, I will export this netlist once more, generate netlist, save, replace, and let's try to load it one more time. So Pcb Editor. On netlist, yeah, and it can find the ones that we assigned, and it cannot find the BT1, which is the battery holder that we know we are going to design it from scratch. So that's fine. We click on Update PCB and close it. Now we have this bunch of components this bunch of footprints that are connected together. And I will click outside the selection to unselect all of them. And then you can use similar tactics as in the Schematics editor in order to select them. But in the PCB editor, you won't be able to drag them right away. You will have to hit M separately in order to move them. And you can use R in order to rotate them. And you see there are these white lines. So these white lines are the actual connections, so where the copper should go. But before you lay down the copper traces, you can move them around. Also, so when you hover in the copper itself, so the pads, and hit M, then it's going to move component together with these additional features like the annotation and also the name of the symbol. So if you hover one of these separate features and then you hit M, then you will be able to move them separately. But if you want to move the component together with everything, then you need to hover one of the copper pads and then hit M. The same goes for this integrated circuit here. Like this, and that, and here you can lay it out. So it's you can play around with this, but yeah, so this is how you do it. But before we lay down the traces between the symbols, we want to create the battery holder, and in order to create that, we will need to go to the footprint editor here, and we are going to select, first of all, we need to add library, so which is our custom library. No, we need to create a new library, because this is a separate thing. So for the schematic editor, we need to create a library for schematics. But for footprints, we need to create a separate library for footprints. So we click on New Library, and you see it also has not lib, but it's pretty. Yeah, it's another file extension. Yeah, and again, KiCad is going to ask us whether it's global or for project, and we just need it for this project. So hit that and click OK. Here we have the BLINKY library now. Now we can create a new footprint. So we go to File, New Footprint, Footprint Name. Yeah, for the footprint name, we need to understand a little bit more about a battery holder. So let's see. So it is called the coin cell retainer for 5.8 millimeter batteries. So let's use parts of those. Retainer, it's such a weird name for a battery holder. So let's do it so like this. Bat holder, 5.8 millimeter. Okay. So yeah, we have now a battery holder for coin cell battery, 5.8 millimeters inside of the BLINKY library, and in a similar fashion as it happened with the schematic, with the new schematic symbol, we have these references here, so we can move them around in order to make space for the actual design. And for the design, again, we'll need to look at the drawing a little bit. So it's nice to have this separate footprint design over here, so we can make it even smaller. Yeah, that. Move it over here a bit more. See, we can see all the numbers, so we cannot really use them directly. We will need to do a bit of calculation. But the most important thing in the footprint editor is the add pad tool. So when you click on that, you're going to be able to place pads. So by default, it's a through hole pad, and then you click and you can place.
I see footprint name. Is it package TOSOT SMD?
It was SOIC. SOIC. Wait a minute. Package outline SOIC, and then 8 and N. If we go back somewhere here and go to the so here, so this is the one. So SMD packages SOIC 8N. Okay, let's go back here, and no, not this one, another one here. Okay, so what do we do now? There's no way to change this on the fly, so we go back and select the selection tool. So yeah, and we can move this around, of course, by hovering and then hitting M, and moving. And then you can edit it by hovering it and hitting E, like this. It will let you to change the pin number, which is a necessary thing to do for the later steps. Then you can define the pad type, which is in our case is going to be SMD, and the shape of it is going to be rectangular, like this. And then here in the drawing you can see also its size, so it's 1.52, and yeah, by default it is already 1.52. Remove a fraction of it, and the height of it is going to be 3.8, 3.05, like this. So here, by taking into account this distance between them, so 8.38, so you want the distance from the center of the stage. So for now I'm gonna hit OK. So here the blue lines, they define the center of the stage, so I need to make the window smaller in order you can see what's going on in the back of on the bottom of the software. So here you can see the dx and dy. So when I move cursor around, Then you see when I hover at the center of the stage, so where the blue lines are crossing, then dx is 0 and dy is 0. So it defines that we have our cursor at the center, at the origin of the coordinate axis. And then when you move it around, you see that dx and dy changes. So you see the dx is increasing when I move it to the right, and dy is decreasing when I move it upwards. So it has a really interesting coordinate axis. So you need to take that into account. And then we want to place this component precisely, so somewhere on the precisely on the 0 axis, and precise, so a specific distance from the center of it. And in order to do that, we are going to make a small calculation. So we are going to divide the distance, 0.38, with 2. And we are going to subtract the half of the width of the component from that. So minus, so 1.52 divided by 2. So we get 3.43. Now when we open it up in the editor, we can specify the position x in precise values, and it's going to be 3.42. And we hit OK. And if we use this measurement tool here, then we can also check that. So here we can see that it's, it's not snapping perfectly, but yeah, it's about the size that we just defined, so about the distance that we just defined. I saw that in earlier versions of KiCad they didn't have this measurement tool, but now in the later version it has it, and it's really useful. It feels like very useful. Let's check again. So yeah, the position y is 0, which is fine. And then we want to place another pad on the other side, and we can just hover this and hit Command C in order to copy it, and click somewhere else. Command C. So Command C. Wait a minute. Command C, and then reference point. Wait a minute.
Because it said like select reference point for copying.
Yeah, it's weird. So in every editor it works a bit differently. Here, okay, reference point, and then I can. Command C. That's weird.
Try clicking one of the corners, maybe. Like when it asks that. Yeah, select reference point.
No, corner doesn't work, but wait. Okay, so now I click on it, then Control, copy, select reference point for the copy. And Command V, maybe. So now it somehow worked. Okay, so
it's kind of like the origin point in Fusion, or like point to point move.
Let's try again. So okay,
like,
Control C.
The top right hand corner now. Yeah.
Selection copied.
Selection copied. But it did it. Yeah, okay. It didn't say the same thing anymore.
Okay, once more. This. Select reference point to copy. Now Command V. Now when I hit Command V, then it's kind of. Yeah. Then it pastes. So it behaves really weird. But it works. Then, yeah, you can hover it and hit E to edit it. So when we need to, so we can leave it to 1, but yeah, the numbers should be, so it's very, so KiCad somehow is very sensitive about the numbering. So whatever is going to be number 1 is going to, it's going to require to connect to the number 1 of the schematic. So but we need just a few connections from the battery holder to the actual circuit. But let's deal with that later. So now the position, so position Y is O, so 0, and position X is going to be the negative number of what we used for the other pin, so minus 3.43. I'll just check whether I entered it here. Yeah.
You're up 4.
In the other one. Oh, yeah. Okay. So like this, and then there are these 2 other pads, 2 additional pads. For those, let's place. So they are slightly rotated. So we can see that there's a 71-degree angle between of them, so which means that we need to rotate each of them halfway. So let's see. First, let's set the size of those. So which is going to be, so width is 178.
That's position though.
Oh, yeah. Sorry.
Down.
Yeah.
Yeah.
178, and then 1.64. And here we also can set the orientation. So 71 divided by 2 is 35.5. This, and also rotated in the right manner. So, okay. Now we can just grab it and position it, because it, it doesn't have a precise position for this. But also, if you take a look at the drawing, then you will see that the footprints are actually bigger than the component itself. So it accepts a certain amount of tolerance. So you can. So it expects that you are not going to be able to place it 100% on the pads, so there's always going to be a bit of an offset. So yeah, you see it's the width is 7.87, and then the distance between the edges of the pads is 8.38, so which makes us it's approximately 0.5 millimeters.
Yeah, it's not that much though.
Yeah, but still it's just enough. So if we miss like 0.05 millimeters here, it doesn't make such a big difference. Let's place another one. So here, hit on E, and for the orientation, let's use the same number, but this time we use minus. Grab it with M and place it somewhere here. Yeah.
And they're not too close. There, I mean, I know it shows. Like, aren't you milling that gap there in between those?
Probably no. So these are all what you have to take into account and with this holder is that all of this is connected. It's going to be the same connection, essentially. And then, so if you place the battery under it, then so the top part is usually going to be plus, and then so the thing that it's not shown here is that there's no pad for the negative.
Right.
And this is what we are going to add at the center here. We are going to add a pad for the negative part of the battery. So no, I'm not. We need to edit it. So for orientation, we type 0, and for size, let's enter 2 and 2. Okay. So this is going to be the negative terminal. And now we need to do some renaming. So let's just choose one of the pins to be number 1, which is going to be plus. So if you take a look here, then the plus has a pin number 1, and minus has 2. And this is what we have to take into account here. So the mappings are going to be made in between these pad numbers. So let's leave this right one as, or the left one as 1, and then this one is going to be 2, but in order to be able to use the number 2, oh no, we can just rename it. I think we can set it to 2. And the rest of those we are just going to, I don't know, can we just leave it without anything? Yes, so we can just leave it without. Like that. Yeah, we might be ready at this point, but then we want also to see like some outline of this one. So we would like to add a bit of aesthetics here. So we want to see where exactly the component goes, and for that we can use this polygon tool, polygon drawing tool, and it's going to automatically activate the silk layer. So it's going to be placed on the, oh, is it? Yeah. It's going to, and with this we can create a drawing of the actual component. We don't necessarily need the pads here, but we would like to see the shape of this. So let's go here. This is needed also to be able to see in our PCB design that, for example, it's not a good idea to place a component next to a component because the outline is gonna touch. Yeah, like this, and then we can add this. You can hit and hold Control in order to help yourself to draw the right angles, straight angles. Yeah, and that's that. We have our component. But I wonder, drawings user, yeah. Now we can go to File, Save, and we can close the editor. And now in the PCB editor, in order to make use of it, before we do that, we need to assign this footprint that we just created to the actual symbol that we use in the circuit. So we need to assign this BT1 symbol to the footprint. So we click on, we click on the Assign PCB Footprints icon here. And footprint libraries, we have 555 BLINKY on the top, and battery cell. And on the right side, we see that there's our bat holder coin 5.8 millimeters. Double click, and now it's assigned. So apply, save, schematic, and continue, and OK. And now we can go. We need to export the netlist once more because this is where the mappings are saved. So we generate netlists like this, and we override the existing netlist 555 blinky.net. Replace. And then we go to PCB Editor, and we load the netlist again. And now you see that there are no error messages. We can update the PCB. Yes. Close. And yeah, KiCad is kind of smart. It also doesn't destroy what you did before. It just lets you place the new component here. And yeah, and we have our board now ready for laying it out. So that's the tricky part. So we can now, okay, let's see. So we are around the center line like this. So I can just move things around. So as you see, so if we would assign numbers to these, KiCad would expect us to. So it will show the white lines in between those, and we would need to make connections between all of those. But since we have only two assigned for the voltages and everything, so for the connections, then it's just going to ask us to connect these, not necessarily everything else. Of course, if we want maybe the the battery holder to adhere to hold on to the PCB much stronger, then we could maybe add some more connections around it, or yeah, and then it wouldn't make sense anyway. But yeah, yeah, you can use the rotate tool in order to rotate it around. So M to grab it and move it, and R to rotate it. Here, for example, no, what? I didn't want that. No, R like that. Capacitor. So let's try to make it as compact as possible. Battery holder, and we have this one. So which is the LED? It's going to be somewhere here.
Are there like alignment tools?
Yeah, so this grid, so you can specify the grid.
Okay, but you can like select multiple models and then just kind of right align everything.
Haven't tried that. Haven't seen anything like that here. Yeah, it's not as sophisticated as like graphics software usually.
Yeah.
I think there are some auto routing tools which goes beyond that, beyond the aligning. But the aligning here works mostly.
Yeah, on the grid.
Yeah, with the grid.
Very
And for example, this we could rotate in 45 degrees if we would want. In order to do that, you go to the editing, and here we can enter a specific value, 45 degrees. Okay. Maybe minus 45 in this case. Yeah. It's gonna be somewhere here in the corner. Okay, so somewhere here. And we don't necessarily need these names, so which means that we can hide them. Yeah, these ones. And we do not necessarily need the silk layer, so this one. For now, it would be nice to have it because of the placement. And then we could place the traces by using the route tracks. So these white lines, I think it's called the rat's nest. Was it the right name? Rat's nest, yes, rat's nest. I'm not sure what it stands for, but it's the rat's nest. Do you know, maybe?
I just thought it was just because it's a huge mess that like rats would make.
Rat's nest. Okay, maybe, yeah. I think that's also what comes into my mind first, like rat's nest.
I'm not one of these guys.
Yeah, and then you would design by using this rat's nest as a reference, so you would connect it by using wires. So these tracks, and so once you activate this tool, you can click and drag around it, and it's gonna help you to route around the existing components in order to find the right connections. But the problem with this now is that we need to understand what is the minimum size of the tracks that we can choose. So for example, if you use the PCB milling technology with the Roland MDX that we have here, like the smallest bit that we have is 0.2, but normally, sorry, in the Fab Academy, people use 0.4. So we have 0.4 millimeter single flute bits for PCB milling, which means that the traces and also the spacing in between the traces should be 0.4 millimeters. In order to change that, we can go here to this menu which says track, and there is a item that is called edit predefined sizes. You click on that, and then here where you have design rules and tracks and vias. So for the tracks, you can click plus and you can enter 0.4 millimeters like this. We are not going to use any vias or anything, so we can leave these empty. But then for net classes, we will need to add a new net class, which we can call like Fab or whatever else. So on clearance, we'll specify it to be 0.4 millimeters, as this is the diameter of our drill bit that we are going to use. For track width, we are going to set 0.4 millimeters as well. And for the other ones, it doesn't matter really. And then here, so these are all the nets that are listed, all the connections in between the parts. And we want to select the Fab net class here and assign to all listed nets. Okay. And this will let us to not worry about the spacing so much, because you see now it's the perfect, like this, the size, like the width of the track, so the one that we want, and the gray area around is showing the clearance. So I would go somewhere here like this, and yeah, from here it's should be really easy to connect all these together now. For example, we could go here. So the nice thing about SMD is also that you can go under the component and connect the trace, something like this. Now we have to go somewhere here. And the layout could be always better, and now we are doomed because this 3.3 volt should be connected also here to this 3.3 volts. And what do we do now?
You could do the one. You could the resistor, the C. You could reroute that maybe a bit more. Yeah, that one. The resistor going to the 555 timer. What about that? Couldn't we lower?
We could put it on the other side actually. So let's delete it. Where do we have the deletion tool? I think you can just click and delete. This is much nicer than in Eagle, that you can just select the lines and hit backspace and it's being deleted.
You could just gamify this and then make people do your auto routing for you.
Yeah. But yeah, I don't know. I somehow enjoy it actually. It's good fun. It's I like the aesthetics.
There's one trace there under the 555 timer. There's a little blip just under the M that's left over.
Ah, yeah. Okay. Let's try again. There's also one. This is connected here. And this should connect somehow to there, and
around the resistor.
Yeah, maybe.
Oh, but then there's the resistor.
You can do tricks like, for example, this C belongs somewhere here. I can hide it also, okay, like that. This connects somewhere here. It should be 3.3 volts, right? G and D. And then
Can you just go under those two resistors on the bottom?
yeah. This.
Yeah.
Yeah. Nice. Okay.
Except then there's that one trace there. Isn't that weird? Like it didn't actually go around.
Which one?
Oh right, because it's connected anyway, so it doesn't matter.
Yeah.
That one, it's cutting diagonally through the.
Oh, I think I see one way how to improve this. So I could just put this somewhere here. Let's say like this, and then we ta-da. Then what else? So we could make it even more compact. Let's somewhere here.
You can like double click on it to just. Just guessing.
Yeah. I have to use it like some. I have been using Eagle so far,
Yeah.
so this is also quite new for me. So yeah, in a year.
There's probably plugins and stuff as well from
Could be.
community.
Let's reroute this a tiny bit. Okay, so here we have this. Okay, it's not perfect, but okay for now. it's gonna be fine. And as the last step, we need to create an outline for it. So let's start somewhere here, and for that we need to connect the edge, select the edge cuts layer here, and we select the polygon tool, and let's create something, battery holder here. Again, we can hold Control or Command in order to create something. Zoom in. Yeah, they are connected. That's nice. And yeah, and this is our board. I can save, and we can export it for PCB milling. And in order to do that, we go to File, Export, SVG, and we need these two layers.
It's just funny, it's still SVG after all that work.
What do you mean? What do you want to have?
No, I mean, it's just because to me it's like a graphic design format, and like Illustrator and stuff comes to mind.
Yeah, I mean, if you would send it out to factory, then you would
Gerber or something?
yeah, then you would export Gerber files.
Can you do that with this?
Yeah.
Okay.
I haven't done it myself yet, but
Okay.
I think we should go over this and order some. Yeah, try out the flow.
Yeah, yeah. Wait, did you export it now?
No, not yet. So you go to Export SVG. So there's we need the like front copper layer and the edge cuts. So we needed black and white, and then we need the board area only. This is usually clicked by default. You need to uncheck this, print board edges, and then one file per layer. So that's what we need. And output directory. Yeah, it's gonna just have it out. Yeah, that's use the relative path. Yes, and export. And now it has it there. We can close this. Now where I had it.
KiCad BLINKY?
Yes, here. Pretty.
Yeah, that's SVG files, right?
Looks like that, right?
Yeah.
Yeah. So it's the and edge cuts. Okay. And now we can use these with this Fab modules that we use for PCB milling here at the lab. No, not Fab Academy. Fabmodules.org. We can go to input format and select drawing SVG, and then we go to desktop and KiCad BLINKY, and there we have the CU SVG. We hit open, have it here. So it's kind of not nice resolution, but we can increase the DPI to 1000. And we can select output format, which is going to be the Roland mill. And for the process, so this is PCB traces. So with a 146 tool, which is 0.4 millimeters. And we also need to invert the image. Because like the black one, the black parts are going to be taken away, milled away, and then the white parts will be visible as copper layers, as the remaining copper traces. And we need to select MDX40 as the machine, and for X we need to add Y, not Y but 0 and 0. The rest of it we can leave as default. Just once more, we can check the cut depth. So I think I haven't tried it with the after you fix the calibrator, but in case you have problems with the depth of the cut, you can set this to 0.2, for example. Tool diameter is 4, that's nice. Number of offsets, this is how much the tool is going to go around each of the traces. So the higher the number, the more the material is going to be removed. And -1 is that all the material is going to be removed. And the rest of it you can leave as default, and then you can hit calculate in order to see how the tool path is going to look like. And this is going to be the tool path for the milling bit. And we can also just save it. So RML file is going to create a folder here and drop it in here. And the same we will do for the other SVG file, which is the edge cuts. So we hit an open. It's 1000 for the resolution. Then we invert the image like this. And output formats, RML, process, PCB outline, machine MDX40. Let's see what it does. So yeah, here it does a weird thing that it cuts around the outline of it, and then also the inside. So in order to avoid that, we need to actually fill it. So maybe we will open it up and I'll open it with the Illustrator. Oh, what happened? What? No, we don't need that. Why is it forcing me to log in once more? Okay. Yeah. Okay. Oh no. Yeah, I'm a bit late with my payment. Sorry about that. That's because of card changes and everything. Now with this, yeah, it's because the outline.
That's tiny.
Yeah, I wonder why. Objects, path.
You have a stroke window in the appearance box on your right. There's the stroke as well.
Yeah. So I need to set the stroke, but so it means that it's not a line, but it's more like a polygon. So what we need to do is cannot really zoom in more.
Wait, what do you want to do?
I just want to fill it all.
Right. Maybe, how about if it's not joined? That's why it's not filling? I don't know.
Yeah, it seems not to be joined.
If you like Control A or Command, yeah, select all.
It's kind of a bit hard to switch over from the conventions of KiCad to Illustrator again. Okay, now. Still, yeah, it's
The top right corner. You can turn that one.
this
no,
one.
the lower one.
I think I did it.
Like the. Keep going. Then that one, and then the one above it.
I think I
the
did
one
it.
above it, though.
I did it.
No, the next one. That one. That's not good. Yeah.
Okay, yeah, you're right. We can do all kinds of modifications also.
Yeah, that's nicer.
But then still it's not filling. I wonder. It's an interesting challenge.
Union, maybe?
Window.
Pathfinder.
Yeah. And this.
I figured this out one day, how to get it. Because it's basically a tiny thin line, right? That's filled. Can't get to Or hey, you can also trace outlines because it doesn't matter. So if you do, you know, the stroke.
That's right. Yeah.
And offset path. I think that's what I use because then it makes a line on the inside and the outside. Maybe. Yeah.
And then if I choose 0.
Yeah. Okay. Yeah, then you still have to select it somehow.
Okay, wait. Clean this. There are like 3 empty groups. How do we? It's such a big action, right? Okay, path. Maybe I deleted the wrong one.
Yeah, because it makes 2, right? It makes one on the inside and one on the outside of the line.
So one more option could be just you can actually see it's in the but it's a line, so it's one single line, so why is it
not filling? I mean, it's not exactly related to the thing, so you could just trace it now, like rebuild it, right?
Let's see, maybe there is like an option.
How about all layers in a single
no, it's gonna just then have that, but maybe
the DPI is too long.
shouldn't be.
Oh.
Oh, Jesus. Maybe I can just open it up in Sublime. These paths, okay.
Stroke opacity 1. Okay.
And these are like some sort of groups.
What's the problem? That it's like a dashed line, or
Fill O. I don't know, like there's groups into groups somehow. I wonder if it will work like this. So there are paths. Just delete these groups. How the generator, I think, is just behaving weird. So this is starting a group, this is ending a group. So let's see, what does this give us to us? Nothing. So, okay, let's just delete these additional groups then. It's interesting, it's 3 groups. 2 of those are empty. Wait a minute. Okay, so this is something already. Let's try to delete this. DPI 1000. Yeah. Okay, there's something, so we simplified it. But then how to make these stroke fill, here, fill opacity 1, 0. No, not PNG, SVG. Okay, so wait a minute, SVG, connect, path. These are comma separated values, or move cursor to an XY coordinate. It's M4672. The line, this is probably the X and this is the Y. How about we put all these in one? This is probably not the easiest way how to do it.
But the problems is that it exported it weirdly.
Yeah, I mean, the best way would be just to try to understand, try to dig into this exporter and then push an update that doesn't do this.
Because what if it was just like a 45-degree angle or something on the KiCad?
No, that was not it.
Because the line looked a bit jittery, or it wasn't, standard angle.
Could be something like this. Yeah, still I'm getting only the line, but then
to just redraw it in Illustrator?
Yeah, but I think I'm close. Line 1010. Move 1010. H90. V90. So 46,207 L, and then just change these M's to L's, and instead of using this group, just use fill equals black, and we are going to use it like this. And let's see, what do we get? Oh, nice. Okay, so it's probably not drawing the lines in the right order. Then from 46 it would go to that's okay, then it would go this is probably the last one. From here it will go somewhere, and this is duplicate. 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 This is also duplicate. 62. Okay, let's see, what do we have now? Okay, a bit closer. 277. Like this is going then down, and then from that position is going, oh, okay, now it should be fine, I guess. Okay, finally. Yeah, we get it. Yeah, learned a little bit about SVG, but it seems that just the algorithm has to be improved over there. And then you have like this inverted shape, and select the output format to RML, process to PCB outline. So this is going to be 0.8 millimeter bit for the machine MDX40. But easy, set 0 and 0, and then calculate. And yeah, and the only problem here, it seems that it's not really catching the edges here. And in order to change that, we can change the size of the tool. So I will trick this a little bit, and now it's going to have that as well. It might be that there's some sort of a offset possible. It's 0.8. Yeah, but it might be that 0.8. Maybe it's possible with 0.6. No. So here in this case you can fake it a little bit, but normally, so there must be a better way how you can do it. Yeah. I wonder why is it like that? Okay, here we have all this paths around, so it's gonna cut through. I'm gonna save this. And we have it here. Okay, so now we have the milling files. So the next step would be to go to the milling machine and try to mill it. So I'm going to try to set up the camera next to the machine, and we could do it actually. So then we would have also the recording of how to calibrate the machine in a way. So yeah, just I'll set it up. So 15-minute break. Hmm?
What's the plan tomorrow?
So to come here early in the morning, and then yeah, we'll prepare everything, and that's it essentially. Okay, so where do we have the tripod? It's here. I will take the camera. Yeah, so 10, I think it's a good time. So, or I'm gonna be here for 9, from 9. Oh.
works.
Great. So
There's
did
just
you,
one problem.
what is the problem?
And the sign-up form, after you put in your email,
Yeah.
it goes to that page that says you're almost done. Please confirm that you want to actually subscribe on your email.
Mm-hmm.
And then it just stays on that page.
Ah, okay. And
Nicholas said there might be a way to do it through the like editing the MailChimp thing.
yeah, we could take a look at it tomorrow. I think. Yeah.
If you refresh the page, it just then it works.
Okay. Well, yeah, refreshing the page is one thing, but then we don't want to stand next to the thing all the time. I guess.
Yeah. But I'm sure there's a way.
Uh,
Inside the configuration for the form.
Yeah, I suppose so.
Redirect back to them.
Oh, there must be. So I'll look into that tomorrow. So
When you turn on the PC, the logins launches the browser.
yeah,
And that's it. It's on the website.
did you set it up also in a way? Oh, okay. So yeah, you set it up also nicely. I will get some extra cables. Okay. So now there's gonna be a disconnected audio for a minute.
I'm sorry, I need to leave.
No.
I think I'm getting cold. I'm freezing.
Okay. Yeah. We kind of solved the issue with the humidifiers, so now it's nicer. So if you would be here 3 weeks ago, then it would be like rain in a cold winter day.
Yeah, my wife and son, they're both sick, so
Mm.
I was the one who was like not supposed to be sick.
What happens here? Looks like we should be. Yeah, looks like. Are we back? Can I hear myself? Yes, I can hear myself. That's great. Now, camera. I haven't connected it yet. Sorry. Not sure yet. Okay, here we go. Here we have the milling machine. See you. Yeah. Nice.
Do you need help with something?
I don't know, maybe you want to see how it's
Yeah,
how the milling works. Okay, do we have all the parts? Here, okay. So we are going to try out to mill the board.
Very curious about it.
For that we also, so we are going to transfer the files after, because like I still have them on my my drive. But we start out with with choosing the right bits. So I think we're just gonna mill the traces for example today.
Yeah.
So the bits for the MDX machines you can find here, and these are the small bits that I got from Damen CNC in Netherlands. So there are also labels of what are the size. So mostly these are flat end and ball end mills. So we are going to choose one that is. So you have to be careful with this packaging specifically. Like I think I broke one of the 0.01s already. They're really small and really fragile. So you have to be So what I have discovered that works really well are these 0.4 millimeter one flute ones. So in order to get them out, it's not an easy task really.
Right.
Yeah,
It doesn't fold out.
Yeah, it doesn't fold out. You have to somehow remove it. Okay. You take it out. You carefully close it and you put it back. So this is the 0.4 millimeter one. What do we need to do? We need to put it inside the collet of the milling machine. So the reason why I have this soft thing here is that I could put it under and put it here so I don't break the tool right away. And the collet is not yet there. And we also need to, so we have.
That was me.
So there are different kinds. So there are bigger ones and smaller ones. And for this, we need a 3.125 millimeter one. So actually, we should take a measurement device and measure it carefully.
125.
I think this is the bigger one. So.
Oh right, yeah, because it's this for the
Yeah.
base size.
But this is a bit too big, it looks like. So this is probably not it. But then there's a slight difference between these two, I think. Yeah, so let me. Yeah, this is too small, it doesn't fit in, so that was the right one. Actually, so you put it in.
It's called collet.
Call it.
Yeah.
Collet. Yeah.
It's like a
New
French,
sound for
like
me.
a French kind of
Okay.
thing. Like ETTE, collet.
Call it.
Then
It's like
you
a
can
name of a girl, kind of.
then you can put it in here. And it's not enough with the fingers that you hold it. You need to use these tools. Now, so you have to be careful not to hit the tool itself. So, and it goes clockwise, like that. So you have to grab the, oops, almost. You see, it's very easy to break the tool. Yeah. So it should be it. So now we have the tool in place. And we can close this. Close also the window. And we can turn on the machine. So this is done by then with this button here. But it doesn't work because is it connected? Or maybe I just have to.
Everything looks like it's plugged in.
Ah, here. There's another power switch on the bottom, on the other side. Here. Turn it on. Yeah. Then with this view button, you can control the position of the build plate, but now it doesn't do nothing. I wonder why, because normally when you press the view button, it should view the model. Yeah, first things first. So in order to mill, we'll need material for milling. So our PCB board was really small, which means that we are going to use one of the smaller copper covered clads. So these are FR1s, so which stands for fire retardant 1. So it's the lowest level of fire retardant boards. And normally in the PCB production, FR4s are used, and these are a bit more greenish. And they are really toxic. You shouldn't breathe dust of this yourself neither, but then if you do, it's not that dangerous as it would be if you would breathe FR4 dust, which is glass fiber basically. And in order to put it to hold it down on the build surface, you will need double-sided tape, and this is what we have here also. This yellow tape is good enough. So we do it, yeah, perfect. Read my mind. And then I think just this one is gonna just enough. It's just exactly that.
No, but
Yeah, maybe you can hold it. It's usually nicer to do it with a knife. Oh.
It's like sticking everywhere.
Yeah. Okay, should be enough. Can you hold it one more time? God. Yeah, scissors are not really the best. Yeah. Then you can remove the double-sided tape as you usually do with double-sided tape, and then now it would be nice to now you press the view and it comes.
It's ready.
Yes. So here now I'll open this up, and I'm just gonna put it here in the corner, and we'll align to the other lines that I have from the previous cuts. So now it sticks nicely. And now I can close it down and I can activate the software. Can you see the computer in this? Not so much. I can move this closer. It's not gonna be the best view, but maybe something.
Should I just bring it up?
Finish. So we need to use software that's great. Yeah, that's perfect. It's much better. So with the Modella, like the MDX 40, we can use software that is called the vPanel. Where do we have it? So it's a little program that is basically the control panel of the machine. And what you can do, you can move the tools X and Y axis like this. So you can position it above the PCB. It's going to be milled. So now I have selected the high-speed profile. So when you're moving the Z-axis, you should maybe switch to low speed here. So you move the Z-axis a little bit down. So with a bit more simple machines like the SRM20, you would use this feature to manually calibrate the machine. So calibration in this case means that we need to set the X, Y, and Z origin. So it's the point where so to set the reference point, so that the reference point is the same as in the design or in the toolpath that we are going to feed into the machine. And usually it's the bottom left corner. So we can move the X and Y axis. So for this I can choose the high speed profile. So at a higher speed there, at a higher speed over here. And maybe Z-axis first. I will move down just to see where do I have the corner. I don't need to have it exactly on the corner. It could be a little bit inset like this. And then the important thing here on the interface again. So let's take a look. So there's this set Hex Origin, and when you have it set, so the drill bit at the location which you want to be the origin, then you hit apply for the X origin, and you select the Y origin, and you do the same for the Y. And then for the Z, we are going to use the sensor, and let's set up the sensor. So first I'm going to move the Z-axis up so the sensor fits in. Machine coordinate system. And I'm going to move it a little bit to the left. now to the right, in order there's enough place for the sensor, because the sensor is quite big. Like this, and then up. And yeah, now we can place the sensor below the milling bit. So it's this thing here, so we place it under. So basically what it does, so the machine is going to try to move the tool down, and when it feels that there's an electrical connection, it's going to stop the motors and automatically set the Z axis, the Z origin. So now, so here, if you could point the camera here, so we have the set Z origin thing here, and so we select that and hit on detect, and then continue. And now here it's gonna move down slowly. Yeah, now it's set. So okay. And one thing that would be nice to do before starting, in order to check whether the calibration went successfully, is to move it to Z origin here, like using the low speed. So hit move.
The sensor's still there.
Yeah, the sensor should be removed.
Because it would try to go through the sensor.
Yeah.
The,
Okay, that's
like the surface of the.
Now, yeah, let's try it one more time. Move to Z origin.
Oh yeah, sorry, thanks.
But now it shows that it's at 0.
Oh. So
Interesting.
it didn't calibrate it.
Somehow, yeah. Wait a minute. Let's try to set the sensor once more. Detect. Continue. On. Okay. Oh no, the sound is back. Okay. Oh. Okay. There's something missing, but I think one should do this PCB milling as a separate thing anyway.
Yeah, yeah, and yeah, with like screen capture on that, and then maybe lights inside because there's a lot of glare coming from that. It's even hard to see.
Yeah, and like with some more cameras. I want to get this wireless camera that I could put anywhere, and then it would really improve things in terms of showing how the machines work.
I think a LED strip inside there, or actually even a light. I don't know. Somehow.
But since these are transparent, you can just put something here and there, like the little LED strips we have.
Yeah. Yeah, I think that helps.
Okay, so the second iteration is ready. Let's remove some dust. Okay, looks much nicer. And then now we could load the other tool and try to cut it also. So the other tool is going to be 0. So where do we?
I took the tools out. I think it's
here. Okay. So we're gonna use the 2 flutes 0.8 millimeter one. So this one. First, let's remove the previous. So again, I'm gonna use this one in order to not break it. And I'm gonna use these keys very carefully, not to hit the drilling bit. Now I need to go counterclockwise like this. Yeah. And I'm going to put it back carefully. Oh. Here we go. It's there. So which one is the 0.8? Okay, this should be it. Okay, let's put it in the collet like this. Let's push it like 1.5 centimeters deep, like that. Let's see the tools to fasten it. Now we'll need to redo the Z calibration. So let's move it back to above the board. So at this point, when the X and Y calibration is set, we don't have to reset it once more because we will use the same origin point for cutting the board out. But we just need to redo the Z-axis. So in order to do that, we'll place the sensor here. Make sure that everything is clean under it. And in order to be able to activate the Z calibration, we need to close the lid. And then again, here still we need to hit quit cutting. Okay, then we need to go to Hex Origin using sensor, detect, continue. Yes. Okay. Let's remove the sensor. Now we can load the other file. So we go to cut, we clear the previous one, and we add the edge cuts. And we open it up and we hit output. So this is now with the 0.8 millimeter bit.
So do you have to put like the step down stuff?
No, it's, yeah, in Fab modules there's a place where you can define that.
Okay.
And this is now 0.6 millimeters, so it does 3 passes before it cuts, because the board, I think it's 1.6 millimeters or 1.7, and then 0.6 millimeters is a single pass, and then it does 3 passes in order to cut through.
So the 555 timer, it's like pre-programmed and everything.
There's even no program, it's just a circuit that consists of some components inside.
Okay.
And it's it has just hard-coded hardware logic on board. Okay, here we go. So now we can remove it. Maybe you have the knife. Great. Oh, it's
Nice.
perfectly cut through. Yeah.
Yeah, didn't like that.
This is what we got. So yeah, the next step would be to solder the components. So, but I'm gonna stop now. I'm just gonna show you the ready board next time. So next week, yeah, check it out. And
Oh, so cool.
thanks for watching, and see you soon.